Welcome back. So in this problem set, what we are going to be doing is working with, again, acids and bases. And I've got a couple problems for us to look at today. So we're going to get started with this first one here. For those that have the worksheets, it's POD 28. Now, in this particular problem, we're going to arrange the following solutions in order of decreasing pH. Now, so we're given a list of compounds: nitric acid, potassium cyanide, sodium chloride, hydrofluoric acid, and sodium with the amine group on it. And the thing we need to do here is establish, strong versus weak, and looking at whether the compound is going to even be representative of an acid or base, or have those properties of an acid and base. So one of the first things I'm going to do is just talk about the difference between strong and weak. So there are 8 strong acids that are and 8 strong bases. And so now that's a list that you can probably look up online or in your textbook. And if it's not on that list, then it's going to most likely be a weak acid or a weak base. Now, in this particular problem set, we have several compounds to look at. So let's talk about, so HNO3, I'm going to go ahead and circle that one, because HNO3 is one of those acids that are a strong acid. So we're going to go ahead and write this out here. So HNO3 is a strong acid. And are there any other strong acids? Now HF is one that typically gives people a problem, because they'll think that, oh, it's a strong acid because it's right next to hydrogen, right next to the chlorine and the nitrogen on the periodic table. And so, not true. HF is actually a weak acid. It's a strong weak acid, but still, nonetheless, it is a weak acid, so it's not going to classify as a strong acid. There are no strong bases, because strong bases are involving hydroxide ions attached to either group 1 or group 2 metal. Again, you can look up that list of those metal cations to know exactly which ones they are. So first of all, we're going to try to figure out the order of decreasing pH. So decreasing pH, the lower the pH, stronger the acid. So therefore, HNO3 is going to go ahead and get placed into the very right hand side, and mainly because it is the only strong acid that's going to have the lowest pH. Now, second is we're going to look at the HF now, because we said that it's a weak acid, and there are no other weak acids. The NH2 group is a basic compound. All right, that's more like an amine. And then the KCN is based off of hydrocyanic acid. So cyanide would be represented as a conjugate base in that case. So this is a basic compound. This is a basic compound. And all this goes back to the salts acting as acids and bases, having to understand where they came from. So just to give you a little short discussion there, HCN is hydrocyanic acid, and the cyanide itself forms CN-1. This is your conjugate base. And so HCN is a weak acid, which means that the conjugate base cyanide is going to be a strong conjugate base. And so the potassium, the ion potassium, is actually a neutral ion, so that doesn't matter. It's the cyanide group that makes the difference there. And so, as we get into that, that's important to understand. Now, the sodium chloride, which is next, we haven't talked about it. Sodium chloride, well, the chlorine itself comes from HCl. All right, the chlorine is the conjugate base of HCl. Now, HCl is a strong acid, which means that chloride ion will be a weak conjugate base. And any conjugate that's weak is not going to have any effect on the pH of the solution. So therefore, this NaCl is neutral. So right now we've established 2 different points. The HF is your weak acid. There's no others. So you're going to put your HF next. And then after that, you're going to have your NaCl, because it's neutral. And not that it goes in the middle, but it does in this particular case because it's not a base, it's not an acid, it fits right in the middle. So we have two bases to work with. We have the KCN and now the NH2. So of these two, anything that typically has a nitrogen is going to be a fairly stronger base. Not necessarily a strong base, but just a stronger weak base. And so in this particular case, the NH2 is going to be a stronger basic substance than the cyanide group is going to be. So KCN is going to go here, and then you're going to have your NH2 compound here as you're having the highest pH in this group. So what do we need to do here is anytime you're working with a problem with trying to range or determine if it's stronger or weaker, you have to go back to the root, especially for those basic salts that involve you to have to think about, where do they originate from? And that compound that they did originate from, was it considered to be a strong acid or a weak acid, or in the case of a strong base versus a weak base? So we have another one that we're going to look at here, and this problem is similar. So it says, which of the following solutions has the highest pH? So now what we need to do is we're given two different compounds versus a bunch of compounds and have them rank them. Here we're just going to figure out which one has the highest pH. So in other words, which is the stronger basic solution of the two. So the first part in part A says a 0.1 molar solution of a strong acid or a 0.1 molar solution of a weak acid. Now, assuming that you've looked at strong acids and weak acids, you have to understand that strong acids are going to give a much lower pH because the concentration of hydrogen ions are higher. So this stems back to this equation: pH is equal to negative log of the hydrogen concentration. Now, you can't just plug in the information, so you can't plug this one in straight into here, because what you'll have to use here, it's a weak acid, you have to use the ice chart, okay? So right off the bat here, when you use the ice chart, you're going to have to go through possibly the quadratic equation, which means that the X value itself is going to be smaller, therefore you're not going to have the same concentration. So the 0.1 molar solution of a weak acid will have a higher pH than the strong acid because of it dissociating much lower in percentage in comparison to the strong acid, which all of it dissociates. And that goes back to the clear understanding of the definition, strong versus weak. Now, the part B, we're looking at the Ka value. So now the larger the Ka value, the stronger the acid, the lower the pH. That's the way you need to remember this, okay? So what we need to do is figure out which of these two Ka's are smaller. Whichever one has the smaller Ka value is going to have the highest pH. Now, the trick to this one is not just focusing on the first number you look at, but also focus on the exponent that you see at hand. What I'm looking at here is the 8 times 10 to the negative 6. Now, if you were just to focus on, say, which one has the largest number, you would look at the 8 and then you would answer the wrong. You'd say that the other one, but focus on the exponent. The exponent 10 to the negative 6 is a whole lot smaller than the other one, which is 10 to, it's actually 1,000 times smaller. So the solution that has a smaller Ka value is going to have the higher pH. So the Ka that has 8 times 10 to the minus 6 has a higher pH for that reason. Now, as we look at problem C down here, we have the PKBs that are provided to us, okay? Now, you can go ahead and convert this into KB just by doing the anti-log function. So I'm going to go ahead and do that now. You could keep it as simple and just go with what we have here. The smaller the PKB, the higher the pH. But you can go about doing this different ways. In fact, that's probably the easiest way to do it. So, but what I want to do is I'm going to go ahead and we're going to use some equations here, okay? So I want to go ahead and get this calculated in KB. So that's going to be 10 to the negative PKB. And then we have KW is equal to KA times KB. So what we're going to do is we're going to get get it back into its Ka form. And that way we can still work with what we talked about in letter B here. So 10 to the negative 4.5. That gives me 3.2 times 10 to the negative 5. That's for the KB. All right, and then for the next one here, 10 to the negative 6.5. That gives me 3.2 times 10 to the negative 7. So now what we're going to do is we're going to convert this into Ka. So Kw is 1 times 10 to the negative 14 and divide it by the Kb. And that gives me 3.1 times 10 to the negative 10. And then we have the last one. That gives me 3.1 times 10 to the minus 8. All right, so now we can look at the Ka values. And we see that, so we're looking for which one has the highest pH. So again, we're going to find the smallest Ka, which is this one here, which reflects back to the 4.5. So the pKb that has a 4.5 is going to have the higher Ka, meaning that it's going to have the higher pH. So keep in mind that you could use the pKb. Smaller Kb, or pKb in this case, represents a stronger base, which gives you a higher pH solution. So those are the two problems that I have for you guys today in this problem set. So if you have any questions, you know what to do. Thanks for watching. See you in the next one.